Over the last few decades, global climate action has mobilized an astounding amount of capital. We are talking about multiple trillions of dollars invested worldwide into major environmental projects and green initiatives. This chart contrasts global financial investment on one axis with global greenhouse gas emissions on the other. Despite the curve for climate spending shooting sharply upward, the line for global emissions continues its climb, largely unaffected by the scale of the investment. A significant portion of that capital is absorbed by logistical coordination. International climate summits, for example, have grown into massive administrative operations, now drawing upwards of 80,000 attendees at a single event. Curious, this level of spending on summits and coordination creates a significant opportunity cost. If the funding required to move and house 80,000 people were redirected toward applied engineering or localized infrastructure, the physical outcomes would likely look very different. When the primary output of these trillions is consensus building and compliance reporting, the resources remaining for actual physical engineering are stretched thin. The focus shifts from solving mechanical constraints to managing the process itself. To understand where that physical focus is missing, we have to look at what policies actually target. Right now, carbon dioxide dominates both public debate and international funding, but not all greenhouse gases behave the same way. Methane, for instance, traps over 80 times more heat than CO2 over a 20-year timeframe. A massive share of this methane comes from specific concentrated sources, primarily waste management facilities and industrial agriculture. We already have the technical capacity to rapidly pinpoint and mitigate these localized methane leaks. The detection technology is highly accurate and ready for immediate deployment. Because these gases are so potent and short-lived, stopping a single industrial leak provides a direct effect on temperatures within our lifetime, an outcome far more immediate than a century-long plan for carbon sequestration. Current policies also frequently place the burden of emission reduction on the end consumer, advocating for daily behavioral shifts to solve a structural problem. For many structural necessities, like long-distance freight, global shipping, and critical supply chains, viable low-emission alternatives simply do not exist at scale yet. The alternative is a physical overhaul of our global infrastructure by producers to reach net zero. Rebuilding the global grid and scaling up energy storage requires massive volumes of critical minerals, like lithium, copper, and cobalt. Those requirements collide with the physical reality of return extraction capabilities and a severe shortage in the specialized, skilled labor needed to run these sites. Mandating net zero targets before securing the raw materials, the workforce, and the supply chains doesn't accelerate the transition. It turns environmental policy into an economically unsustainable aspiration. This disconnect between policy and reality extends to energy accounting. Many companies purchase green certificates to claim their corporate operations are running entirely on clean energy. This diagram illustrates the physical laws of electricity. By design, electricity always flows from the nearest generation source directly to the point of demand. Purchasing a financial document from a distant renewable project does nothing to alter that real-time physical flow of electrons. Financial mechanisms can influence investment behavior over time, but they cannot override the laws of physics, making many corporate accounting claims physically inaccurate at the moment of consumption. Beyond atmospheric temperatures, several other environmental thresholds determine the long-term stability of the planet. Threats like biodiversity loss, rapid land degradation, and freshwater stress pose immediate risks to global food resilience. In many regions, these issues are more pressing than near-term climate shifts. Environmental stability is not achieved by focusing on a single variable. It requires a systems-level triage that addresses these interconnected risks simultaneously. Overcoming the shortages we've identified, the minerals, the skilled labor, the grid capacity, requires a shift in priority. It means building the physical foundations of a transition before finalizing the political targets. This focus on verifiable capability is the core of a potentialist approach. Tangible progress is defined by what can actually be built, operated, and maintained, like expanding physical grid capacity and deploying reliable, scalable technology. Decentralized physical engineering solutions allow for much faster learning speeds and real-world adaptability than top-down global mandates ever could. Meaningful progress happens when we align our political ambition with our actual physical capability. It is the transition from symbolic accounting to physical performance.